Okay, so now I want to talk about physics results. Now, there are so many physics results I can't talk about many of them. I'll try and pick off the ones that I think are important to give you, at least conceptually, a feel for what we're doing and what we're concluding. Let me start. So I'm going to put this down in, and I'll give you the conclusion on the lead-in slide, and I'm going to number it. Okay, so what have we learned from RHIC and LHC and heavy ions? We actually see, partly as a result of my answer to the question this gentleman asked, that we have a consistent picture of the geometry, at least the geometry, that's straightforward. And now I will also show you also the dynamics and the evolution of these collisions, okay? So the multiplicities shown here, this is the charge multiplicity per unit pseudo-rapidity divided by the number of participant nucleons. So this means if I took a Glauber model and or any other geometrical model that you want to impose, as I overlap or go to smaller and smaller impact parameters, I can count approximately how many protons and neutrons overlapped initially, okay? So that's the number of participants. Now, over here I have the same thing, but it's 0.5 times that. So it's the number of participant pairs, so don't worry about that. These are just different by a factor of 2. Now, here's versus center mass energy, and take a look at this. First of all of the proton-proton data are just gray data here, and you see that all the heavy ion data go up, and it looks, maybe this at the lower energies less than a TeV could be linear. Likewise, the heavy ion data could be linear. At the LHC, we see that there's this sharp increase, and in fact, this probably isn't a linear increase of the charge multiplicity density as a function of the beam collision energy. So this is heavy ions, this is proton-proton. These proportionalities don't really mean anything at this stage. Although theories do a fairly good job just using geometry to fit this. Now, the thing that's interesting, if you plot versus what I will call centrality or impact parameter, you see the largest number of participants, the largest number of nucleons that are overlapping, or the smallest impact parameters, as designated by this symbol here, as compared to more peripheral, which has a less overlap, lower number of participants. You see this distribution, which is interesting because at RHIC, the blue squares, we got a distribution that looked like this. And at LHC, we got in red a distribution that looks very similar. Now, this RHIC data, to be able to put it on a plot with LHC, is multiplied by a factor of 2.14, which is the difference in the multiplicities, okay? Now, what you see is, in fact, that these are surprisingly similar. So as we overlap the geometry, whether it's gold on gold or at RHIC energy or lead on lead at LHC, it's not so different. Now, there may be small differences down here. Up here, it looks like it's, the most central collisions are not very different at all, as long as you scale by the multiplicity, the multiplicity difference between RHIC and LHC. Down here, at more peripheral collisions, there appears to be a difference. As I answered the gentleman's question back there about low X physics, meaning higher and higher energy, lower momentum fraction of the parton, which means parton's a quark or gluon in the nucleus, it could be that, as you go to higher and higher energies, that you get more and more gluons, but those gluons become shadowed by other gluons. So they're not as effective, actually, at producing particles. And it could be that these small differences, where the LHC multiplicities are lower for these peripheral collisions than at RHIC, may be due to something like gluon shadowing for those geometries. That's something we still have to see. And it could also be that somehow the initial state of the collision, whether it's the momentum fraction of the partons in the nucleons in the nucleus, or something else, is affecting this. So this is something that we might learn more about in the proton-Lett data. But this is still something that's outstanding. The other thing I should say is that models, various models from perturbative QCD, including this model here, which has gluon shadowing, do a fairly good job at fitting this distribution. So this means that there's something that is quite similar between LHC and RHIC energies in terms of the dynamics and the evolution and the geometry. Now, we can also look at the size of the system. Here's plotted, there's a technique called, by various names, Hamburry-Brown twist, because those were the two people who, let's say, invented the technique in the 1950s to measure the Bose-Einstein correlation of photons from stars to get the size of the star. As you know, bosons like to be together, let's say. They influence each other. And so if you look at pions, for example, you could do the same and image the final state of the expansion when the pions, for example, pions are bosons, when the pions were created. Just like looking at photons from distant stars, you get the size. Here, you can plot 3 radius parameters that are used in these types of analyses as a function of the charge multiplicity, where to the right, again, are the most central collisions. And one sees that these lower energy experiments, all in black and white here, different energies, have a rising size, let's say, system size. And then, of course, at LHC, the multiplicity is larger. And so what we see is that this volume at the Large Hadron Collider is about twice that at RHIC. And volume, if you take these numbers in Fermi cubed, you get something like a few thousand Fermi cubed, okay? If you put the right coefficients in front. So you can also, from this technique, get the lifetime of the system. And if you plot the lifetime versus the multiplicity or the centrality, the LHC data is up here. The lower energy data increase in lifetime. And the LHC lifetime is about 40% longer than the RHIC lifetime for the most central collisions. So, in fact, as we go up in energy, the system size, there are more particles, system size in the expansion increases, and the lifetime extends out to about 10 or 11 Fermi over C. So, point 2 that I want to make, what have we learned? Turns out that if you take the particle ratios, and then you look at, let's say, a thermal model, assume that everything's in equilibrium and that you make particles when you hit a certain temperature and barochemical potential, which is very low here anyway. That means the number of baryons compared to mesons, for example. That, in fact, you can determine the temperature at which those hadrons were born, okay? So what happens is if you take this is RHIC data, and this is the initial data from Alice in red plus the RHIC data, just for an overlap, but this has been done more extensively now. But I know this looks real complicated. The bottom line is you take the ratios of all the different particles that you identify in these most central collisions, and you then take a model that has as variables, it's a thermal model, just temperatures and barochemical potential. And the models are the straight lines. The colored symbols, open symbols, are the data from RHIC at 200 GeV, gold and gold. These are LHC data, lead in red, and then the RHIC data from over here as open symbols. And there are various thermal models, but in any case, to be able to fit this distribution of the ratios of the different types of particles, one needs temperatures of around 160 to 170 MeV and very low barochemical potential. And you'll notice that the barochemical potential at LHC is much lower than that at RHIC, and that's because you have many more particles produced, and so you have many more antiquarks and quarks compared to any excess that you might have. So these particle yields actually appear to resemble equilibrium abundances at temperatures near that predicted by the lattice for the phase transition. And these are just a few more plots. This is from the lattice, but I'll leave those. Excuse me. Okay, the third point I want to make, we talked about this flow. We saw it at RHIC, that there's significant flow, and I want to relate that to shear viscosity. It turns out that the RHIC collision, or LHC collision, comes in like this in perspective, and then you see the flow being largest in the reaction plane here. As I said, at RHIC, this was predicted by hydrodynamics with no shear viscosity, and I'll show you some calculations with a shear viscosity in. But what happens if you plot this V2, the elliptic flow parameter, you see that it increases sharply, but appears almost linear as you increase the center mass energy from RHIC to LHC. There are other things which we can talk about if you like as you go lower in energy, where this flow actually changes sign. I should also say that at RHIC, they're investigating that in particular because they're able to go down to energies of those fixed target measurements that were made previously. So here's a model, viscous hydrodynamics. These are calculations from Schenke et al., which have been actually, this was the original publication. These results are from a more recent publication. Here, he plots V2 versus transverse momentum for RHIC data and for LHC data. Those are the symbols. And what he sees is that this eta over S, which is the shear viscosity to entropy ratio, is 1 over 4 pi, within errors for the RHIC data. And it's, there's not really a good fit for the LHC data, but it may even be a larger value of 8 over S at the LHC. On the other hand, it's fairly low, and it's similar between the two, and I want to talk about that a little bit more and give you a better intuitive feel for what's going on. Let me first say that there was a paper in 2005 which basically which calculated the shear viscosity over entropy ratio for perfect fluids, and found that there's a universal lower bound, which is 1 over 4 pi, if you have a fluid that flows without resistance. Now, this was done basically in a string theory type calculation, but there have been perturbative calculations since then which come up with a number quite similar to this. The bottom line is to remember this 1 over 4 pi, and you see that we're very close to having a nearly perfect fluid at RHIC and LHC. Now, if I plot this versus temperature, you can get superfluid helium, ultra-cold atoms. They follow as a function of temperature this value of 8 over S above the lower bound, which is 1 over 4 pi. Now, the RHIC data look something like this, and this is kind of an estimate of the uncertainties from the calculation you just saw before and a few others from viscous hydrodynamics. And of course, the thing to note, it's much lower than anything that we know, meaning it's close to this lower bound, but it's also at very high temperatures. It means that quarks and gluons, as we had said already initially from the first observations at RHIC and the comparisons to ideal hydro, where there's no viscosity, quarks and gluons at these high temperatures flow very easily. Now, to give you a feel of how we could even think this, right, it sounds very abstract. Okay, we jumped from elliptic distributions, azimuthal asymmetries to, okay, hydro's fitting it with no viscosity. Now, give me some feel for this. All right, so if you have, let's say you have an overlap in a central collision. It looks kind of central. It's fairly, this is in the entrance channel, the nucleons that are overlapping. And you put it in one of these viscous hydro calculations. This again from Schenke. And you say there's no viscosity. And you say that there's some viscosity of, let's say, 1 over 2 pi, which is twice the lower bound, which is maybe what we're seeing at RHIC. If you look at the evolution, you can see that this initial distribution, you get better resolution if you don't have a viscosity, a shear viscosity. Just looking at this, you see that you have higher harmonics. You have this looks a little bit more smeared out. That's what we're looking at. We look at the final distributions, and we're trying to determine what's going on and what the shear viscosity to entropy ratio is by looking at many events like this, given whatever input we can get on the overlap in the initial state. So anyway, we can decompose this into harmonics and get the different distributions and then try to see if we get a better handle and number for 8 over S. I'm just looking at the time because my voice has about 30 minutes left, maybe, if you're unlucky. Okay, so final observation. 8 over S, 1 over 4 pi. If you have an initial distribution like this, would look like this. If you have ideal hydro, it would look like this. So you could Fourier decompose that and tell the difference. And that gives you information on the sound attenuation length, perhaps the Reynolds number. And so you have to do this higher statistics Fourier decomposition. I remind you that from the cosmic microwave background, they did a tremendous job, right? Because their harmonics, they're able to tell, in 1 part in a million, the differences in the cosmic microwave background. But they went up to hundreds on their decomposition. Okay, number 4, QGP radiation. So if you have a thermal system at a temperature, it's going to radiate, right? And as it does, you would hope to be able to see the photons and determine its temperature. It should be, you know, a Maxwell-Boltzmann, for example. Okay, so at LHC, central lead-on-lead collisions, this is a distribution of photons from the collision that are not from decays, and that the higher transverse momentum part is actually well reproduced by perturbative QCD. This lower momentum part, in fact, is an excess over what's predicted. And if you just fit that with an exponential and say that those are radiated photons, you get 304 MeV. Likewise, at RHIC, you can do the same thing. Fit to perturbative QCD, and then get the excess. You get 220 MeV. So, it turns out this is close to what's expected for temperatures for these two systems if they were in thermal equilibrium. Now, the really interesting thing is that the LHC introduced, in particular with the capabilities of ATLAS and CMS, the ability to measure jets. There were more heavy quarks produced, and so hard probes, in fact, became a reality. So you just saw this nice talk about tomography, but we don't have an external probe, right? We don't have any proton or carbon beam. We don't have lasers. So what we do is we use the initially scattered partons in the collision, see what happens as they traverse the medium to do our own tomography of what the system looked like. So the main thing here is it's important and interesting because these hard probes can be predicted using perturbative QCD because they're large momentum transferred, squared processes, or a large mass scale like heavy quarks. So if you imagine a collision of two heavy nuclei, the probes we're going to use are the initial hard scattered partons, which are partons I use for gluons and quarks. And these could be gluon-gluon, gluon-quark, or quark-quark interactions. And so what happens? As soon as you have a scattering, in particular if you look out to the side, you will notice that, you know, these partons have to propagate through this medium. And remember, the medium, the size of the medium is about 14 Fermi. So we look at the interaction, and we look at these partons when they come out. Now, these partons can radiate, they can scatter, they can lose energy. And in the end, we see hadrons, we see jets, we see high momentum particles. And so we want to look at these observables, let's call it, including heavy quarks, large momentum, transverse momentum partons that become jets or single particles. And so we want to look at this basically in a background of all these other particles. But the high momentum part of the hard process is the signature, and that's where the LHC, which makes has larger cross sections for that, comes into play. Okay, so here's the next question. What happens to partons as they traverse the quark-gluon plasma? So you saw a parton, these guys are hard scattered. What happens as they traverse the medium, Y, and what's the analog in terms of QED? Anyone? Right here. Wait, hold on.
Scatter with the matter which is around, which is supposed to be the GP, and they lose energy irradiating.
Okay, so they scatter from the matter. What's the interaction?
It's still a QCD interaction.
QCD. So I'm going to walk you through this a little bit, because I have another candy bar.
It's called jet quenching. I mean,
right, so this is jet quenching. What's the analog with QED then? QCD, QED. In QED, what do you have? You have charged particles.
Yeah, it might be interaction with some, or if you do the example as before, it might be with tissue. So like what is expressed by the Bragg absorption curve. So you have a dA and dx, which is...
Right, so you have quenching, which means you lose energy. You don't quite have a Bragg curve, maybe for the highest momentum. I take the liberty to keep you online here for a second. Okay, so in QED you have charged particles. You have scattering. You have the electromagnetic interaction. Give me the analog in QCD.
There is the charge of the quark, which is a...
Color charge.
Color charge. Yeah.
Right. And then what's the medium here?
The QGP.
Right. It's colored. Right. Okay, I think that's... There you go. Sorry. Okay, so yes. So you have quarks or gluons fast moving through the medium. The medium has color charge. It's red, green, and blue quarks, right? And gluons. And so it's just like quantum electrodynamics, where you have a charged particle going through any material, right? There's an electromagnetic interaction between charges. Here, there's a color interaction, QCD, between the parton that's going through and the medium itself. All right? Okay, thanks. So the thing I mentioned already is that the cross-sections are much larger at LHC, which would be this energy. This is energy. This is cross-sections for various processes in color. LHC, this is RHIC energy. And you see, high-energy jets just really come up. And you see these are 3 orders of magnitude, each label here. Also, BB bar production increases by a factor of 100 from RHIC to LHC, and CC bar by a factor of 10. So there is an abundance of heavy flavors and large transverse momentum processes at LHC, and this allowed some of the measurements that I'm going to show you. So here's a plot of what's called the nuclear modification factor, which we call RAA. And this is just the number of any type of particle, that's a superscript, produced in a nucleus-nucleus collision, divided by the number that you would measure in a proton-proton collision, scaled by the number of binary nucleon-nucleon collisions in that nucleus-nucleus collision. So you need geometry, you need to know how many participants. You do that with Glauber, and you get RAA. Now, if RAA equals 1, it just means that the nucleus-nucleus collision is a superposition of independent nucleon-nucleon collisions, if RAA equals 1. And we plot this versus, you can plot versus transverse momentum, transverse energy, or mass, what have you, depending upon the particle that you measure. And you see, and I'm going to ask you a question, so I hope you're following. You see that this RAA for lead, for photons, W's, and Z's is equal approximately to 1 as a function of transverse energy or momentum out to 100 GeV for the partons. And for proton on lead charged particles, which is here, Whereas for lead on lead, there's this extreme suppression of a factor of 2 to 5. Now, there's similar results at RHIC for hadrons and photons up to 20 GeV over C transverse momentum. So now, let's see if I did this right. Right, so here's my question. I think I have 1 or 2 candy bars left. Why are vector bosons, these guys, not suppressed in lead on lead? And why are hadrons in p-lead not suppressed? Okay, you have to, so this, I'm going to revert back to Einstein. Einstein said, imagination is more important than knowledge, okay? Use your imagination. What do you think? You don't know for sure, but what do you think? One of them you know for sure. You know everything, I know. Okay, let's try someone else, but then I may come back to you to help. Thanks. Why aren't vector bosons suppressed in lead on lead? We just talked about the interaction. We talked about color charge interacting with a colored medium. What about vector bosons? What's their interaction? Raise your hand if you have an idea. Yeah, right here.
Vector bosons are not colored, so they don't interact.
Say again?
They are not colored, so they don't interact in...
They are not, I didn't get what it was.
They are not colored.
They're not colored. You got it. Okay. So they don't interact strongly, right? I mean, they don't have color charge. And, okay, now I have to take it back because, no. What about the second part? No, go ahead, keep it. What about hadrons and protons on lead? What would you speculate? This is only speculation now. Why, if you look at hadrons and protons on lead, that's these guys, that's equal to 1. Whereas in lead on lead, you know, you see this extreme suppression of high momentum particles. You may have to share your candy bar with somebody. You need help? Do you want to answer? Guess? Okay, we've got a guy in green. He has a candy bar, so, okay.
Well, maybe because you do not have a quark gluon plasma.
Oh, yes, you got it. Okay, good. So yours is safe, and he's got one anyway. All right. So, right, so protons on lead, this is the protons on lead you just saw out to 20 GeV, the hadrons, the charged particles. It's basically consistent with 1. Whereas in lead on lead, as you go from what we call peripheral to mid-central, you have a suppression of less than 2 to the most central, where you have this extreme suppression. So as you get more central, the partons have to traverse more of the medium. This is on average, right? We have it as a function of azimuthal angle too, but I'm not going to show you that because it's consistent with the shapes of the distributions. Okay, so if you look at the combined data at RHIC and LHC, you see that, in fact, depending upon, you know, exactly whether you identify pions or you don't, you only take charged hadrons, no matter what, you get this extreme suppression from the LHC. You get a little bit less from RHIC for these hadrons from star. And then you see it start to rise. Now, look at this scale. It's kind of an inverted semi-log plot. This goes out to 100 GeV for hadrons. These are all hadrons, single particles. And the suppression is there. It's more for LHC than at RHIC. The other thing, I come back to this in just a minute, because you see it rising again at the LHC. But I wanted to also say, so at RHIC, there are many reasons for the RHIC beam, what's called energy scan, going down in energy at RHIC from 200 GeV gold on gold down to 7 GeV. And what they're doing is trying to see if this extreme suppression measured in Alice and in star, so that's the two different energies, and as you go down in energy, what happens, and you see the suppression, let's say, going away, or it's less suppressed, but also then you see this enhancement at the lowest energies. And it turns out that this enhancement was seen at the SPS, which is 17 GeV, it's fixed target, but 17 GeV center of mass energy, this enhancement here, and that has been and it was seen at Fermilab in fixed target proton nucleus interactions, and it was attributed to, and it's called the anomalous nuclear enhancement in the entrance channel, which means that the partons coming in and the nucleons in the nucleus have some already initial state transverse momentum. That's the easiest way to describe it, but it could be other entrance channel effects where you have a radiation before the collision. So anyway, you see this basically reproduces what's seen at the SPS, and what STAR is trying to do is to try and see where the quenching starts to get dominated by the enhancement, and then of course one's going to need models to try and disentangle those two, because you still could have quenching even at this energy, although you have an enhancement. It's a matter of how much of an enhancement there is. Okay, so if I look at that high momentum part of the charge particle distribution and the pions from Phoenix, what theorists have done is they've fit the RHIC data and extrapolated out in transverse momentum to the LHC data. And the one thing that's suggestive is that they see that the strength of the coupling at RHIC is 0.3, but if they use that at LHC, they get too much suppression. And they say that it's better fit. Let's say if they reduce the coupling strength in QCD to 0.27, whether that's a good fit or not, you can argue. But the point is that it may be that this this decrease in the suppression is described by a change in the coupling constant as you go up in energy, okay? For the partons that are propagating through the medium and their interaction with the medium. Now, it could be that there are other effects. Let's just leave it at that. Okay, so I think one of the most interesting things was the observation of this dijet energy imbalance by CMS and Atlas. So as you saw in the cartoon, you have initial hard scattering, and these partons are back-to-back initially. It's a binary scattering, so you have partons going back-to-back through the medium as the medium is evolving, and then they come out, and if they lose energy, then there should be some imbalance in the energy of the jet that the one parton fragments into compared to the other. So what they've done, both at Atlas and CMS, Atlas was first to come out with this. They've plotted the energy asymmetry between the highest energy jet in the event and the next to highest energy jet. And they've required that those be in opposite hemispheres, okay, in phi. So they take that difference over the sum of those two energies, of those two jet energies, that's opposite hemispheres. And then, it's, as I'm kind of waving my hands, the picture's up here basically. So they have a trigger jet of high momentum and then somewhat less momentum in a wayside jet. And they have cuts of 100 GeV for the leading jet and 25 GeV or greater for the next to leading jet. And what they see is an asymmetry in the energy which means that this away-side jet has lost energy, and they compare it to proton-proton interactions where you expect that you have no medium, which are these open symbols, and they see that there's this large asymmetry, and they compare it to some Monte Carlo calculations using perturbative QCD. And again, this asymmetry is definitely significant. CMS sees the same thing. Whereas if you plot the angle between these two jets, it's not so modified. That's the azimuthal angle difference, where this is 180 degrees over here. It's not significantly modified. So those partons propagate through. Of course, these are pretty high energy jets, at least the leading one, and 25 GeV, but the directionality is maintained. Now, if we just look at particles on the left, we saw this for the charged particles out to 100 GeV, this suppression. And we saw this for the W and Z and photons, the lack of suppression. If we extend this over and look at high transverse momentum jets, then we see that inclusive jets are in green here. This is from CMS. Those are suppressed, similar to what the single particles are suppressed at. And even the B jets, which are heavier leading particle jets, which are expected to come from B quarks that are made in the initial collision, are also suppressed. Now, it turns out, for reference, that this range of jet momentum could be related to this range of single particle momentum when you fragment these jets on average. And so, it's interesting and it's consistent that there's this suppression of these jets, which is reflected in the suppression of the single particles. So the other thing is, even at the largest transverse momentum, so it's not, in my view at least, totally understood how you get you get suppression from the interaction in the plasma, but I think there are other questions about heavy quarks and whether they might propagate differently from light quarks or gluons, which you expect, actually. Okay, so where does the energy go? Also from CMS. Here, if you have the trigger particle over here, the trigger jet over here, again, this is as a function of asymmetry, so the asymmetry they use momentum instead of energy between this leading jet and this next to the leading jet is plotted here. As it becomes more asymmetric, here they plot the missing PT, and I should just say that this is on the leading jet side, and this is on the away side, or the next to leading jet side. They see that, since this is negative, that most of the high momentum particles in red here, greater than 8 GeV, are on the leading jet side, and the lower momentum, so that's balanced in the cone of the leading jet by particles of lower momenta, these lighter colors, in the next to leading jet side. So there's some balance, but the composition appears to change of the jets. And if you go outside the cone, outside of these jet cones here, if you look at this kind of hash around the circle, you see that, in fact, you get a lot of low momentum particles outside of the jet cone on the away side. So we're still trying to understand how these jets fragment. If they're very high momentum, you expect them to propagate through the medium, interact, lose energy, radiate, split, what have you, if they're gluons or quarks. And in fact, they will not fragment into particles till they're outside the medium. So we're currently looking at the fragmentation of the particle distributions inside of these jets, and trying to understand this composition a little bit better. So that's called the fragmentation function. Okay. So my last topic before I jump to the future, which will be brief, the future itself, because we're not there yet, but okay. Suppression of Quarkonia. It definitely has the properties of color screening. So what do I mean by that? Well, if you make in the initial hard scattering, you make a heavy quark pair, CC bar or BB bar. So this would make, if there were BB bar states, that would be the upsilon states at about 9 GeV mass or resonance energy, whatever you want to call it, and CC bar, which is the J psi, at about 3 GeV. And you see the mass spectrum here of muon pairs from CMS, and you see the J psi, a little bit of psi prime, the hadronic resonance is down here, and then you see the upsilon, they see the Z way up here, of course. And so what one expects is that if you make a CC bar, BB bar pair in the colored medium, that in fact, the color screening will decrease the yield of resonant J psis or upsilons, because these two heavy quarks are screened by all the other lighter quarks in the medium. So that's what we mean by color screening. Now, of course, at the bound state, if you have confined, if the bound state is tightly bound, let's say, then you have, it could be expressed by potential, which is more binding than if it's loosely bound, which would be something like this. And so, depending upon the strength of the binding of those resonance states, or we could translate into size of the resonance state, we expect a melting order of the CC bar and the BB bar, which has been represented, by a thermometer, for example. The one at the lowest temperature compared to the critical deconfinement temperature, the first one would be the J psi 2s, and then the upsilon 3s. So you see, these are all excited states of the J psi and the upsilon, which are larger. They're easier to break up. So they would be more easily color screened. And then as you get up higher in temperature, the J psi and then the upsilon, which it's not clear that the upsilon, you could even, at least in these collisions at these energies, break up the upsilon ground state. So that's the background for doing these measurements. Now, CMS came along and measured the suppression factor, this RAA, in lead on lead compared to PP versus multiplicity, number of participants, where, again, the right side is the most central, this is the most peripheral, and they see, in fact, a suppression ordering of the upsilon 1s being the least suppressed, although somewhat suppressed, the J psi, and then the upsilon 2s. I remind you of this thermometer, and what they do then is if they look and integrate over all their data, they see the upsilon 1s, and they plotted it versus binding energy for each of these. The upsilon 1s, the J psi, the upsilon 2s, 3s, and the J psi 2s is the most suppressed, which would be the lowest temperature. So they see this ordering, which gives credence to the color screening in the medium of these heavy quark-antiquark states. So what have we learned? This is kind of a summary. We have a consistent picture, as I said, of the geometry, dynamics, and evolution of the system. The particle ratios reflect equilibrium abundances at temperatures near the hadronization temperature, predicted by lattice. It has characteristics of a quark-gluon plasma with ultra-low shear viscosity. The radiation gives us temperatures above the critical temperature, above 170 MeV. It's opaque to the most energetic probes. I just showed you the suppression of jets and high PT particles, the energy imbalance, and that P-lead, in fact, doesn't show this, which indicates that, in fact, there is an effect of the QCD medium in lead, and it has this color screening that I just talked about. So, but, you know, there's still a lot to be done. I'll point that out in just a moment. But let me go to the future. I think I have a few more minutes. Now, I can't possibly go into the upgrades that have occurred just in the last couple of years at RHIC for detectors or the RHIC run plans, although if you ask, I can tell you what they are. Likewise, the LHC upgrades, I think only Elise has a plan that's totally approved, and I think Atlas and CMS have just passed the first stage of approval. The long shutdown 2 of LHC will take place in 2019 or so. But I do want to mention a couple of things. There's a new RHIC experiment, and I'll get back to maybe what RHIC's plans are if you like. And then there's a new machine on the horizon, the distant horizon at the moment, the Large Hadron Collider, or sorry, the Electron-Ion Collider. So this new detector, currently known as S-Phoenix, but it is having its first collaboration meeting in December, and it addresses questions of how do we get from hard scattering at the LHC at low X values, I show you in the next slide what I'm talking about, to the quark-gluon plasma degrees of freedom. So it was thought that at RHIC energies, this would be quite important to do and to contribute to all the data that we have from the LHC by measuring jets and upsilon states at RHIC. So the whole idea is to probe the different scales of the medium. So this is, maybe it's not so complicated, but let's do it. If you had the critical temperature here, or twice the critical temperature, which is kind of still a little bit below the initial RHIC temperatures, and then LHC temperatures are up here, and you plot the microscopic resolving power in 1 over Fermi. Now, jets that pass through the quark-gluon plasma at the LHC are expected to have some schematic trajectory like this as compared to those at RHIC. So why are these different? First of all, let's see, maybe I even ask a question. Yeah. So I think I have one more candy bar. So I won't tell you the answer yet. So what happens? I'm trying to think of how I do it without telling you the answer. Okay. So the question is, how do we get, to this medium from the initial scattering up here at these that occur at high temperatures and different resolving powers for RHIC and LHC? And before I really tell you about this slide, let me ask you the question, then we go back so you understand it better. So why do jets at LHC actually have a higher resolving power? Why on this axis in 1 over Fermi is this higher at LHC than at RHIC? Why do you probe, so I'll ask it differently. Why do you probe smaller distances, separations? Okay, go ahead. Use the mic. Say again.
The average energy per nucleon is higher. So like you said before, you look at the smaller structures.
Right. So you go to lower momentum fraction, lower x, and therefore you get higher resolution at, at the lower x. You have a candy bar already, right?
No.
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 Oh. Pasquale, so I don't kill someone. Oh. Okay, now you can go to sleep because I'm out of chocolate, but I'm almost through anyway. So, look, right, so because you're coming at higher energy, you can probe smaller distances or separations, so therefore you have higher resolving power. So you're coming in at very high energies, and how do you go from there? And I think this was one of the questions during the question period, and end up, with some thermalized medium. We don't intrinsically know how that happens, and we want to understand it. So we want to measure jets at, by probing at this lower x, or lower energy at RHIC, and see how this evolves in temperature and how the medium evolves. And at the same time, which hasn't been done with any decent resolution at RHIC, measure the upsilon melting that I talked about in the very last slide, which really looks at these temperature scales with much lower resolution. Lower resolution because these states are big compared to, a hard parton scattering. So the different size states of the upsilon actually will give you information down here at the thermal scale. So this stuff really hasn't been done at RHIC. So that's the plan for this new RHIC detector, which is going through conceptual design and approval and is expected to run, it had better run in 2021 to 23 because the next thing I show you will be coming along right afterwards. But again, so what's new here? It's high rate data acquisition and both electromagnetic and hadronic calorimetry inside the Babar magnet, which was moved from SLAC and is now at Brookhaven. So it's going to have tracking on the inside to do heavy flavor tagging, and both electromagnetic and hadronic calorimetry over large solid angle to maximize RHIC running so that measurements could be done like the ones I showed you from the LHC, but at RHIC. So the last thing I want to mention is what's pushing the previous experiment, and that is that the US nuclear physics community just endorsed as the next machine to build for nuclear physics an electron-ion collider. And the goal is to start construction in the 2023 to 25 time frame for completion sometime probably between 2025 and 2030. Okay, so I point this out. There's a recent Scientific American article about this that basically anybody can read, your friends too. The bottom line is that on this continent, and some people in this room actually did measurements in the 90s which showed that at Hera up in Germany that there's an abundance of soft gluons inside the proton. We talked about this at low X. I show you a plot next. And the role of these gluons in nuclear structure and the dynamics in general really isn't known or understood now. Also, the nucleon spin and distributions of quarks and gluons are still a mystery, after decades of study, even these studies at Hera. So, there's a list of science questions. Let me call your attention over here. This is what we've been talking about. If you take the overall momentum fraction carried by the parton, you see that the gluons go up very quickly. And if I tell you what the X, this is X that I've been talking about, the X range at RHIC is in here, the X range at LHC is over here, and the X range at an electron-ion collider would be down here. So what's going on? Well, there are many science questions. can we understand the role of gluons in terms of their spatial and momentum distributions in the nucleon and perhaps in the nucleus, but mainly in the nucleon? Can we understand the spin components of the nucleon? Those aren't understood. How do we get from that to nuclear binding? Is there saturation? As you go to higher resolution in the proton or in the nucleus by probing with electrons at very high energies, so it's an electron and an ion colliding at high energies, is there saturation of the gluon density? Is there a color glass condensate? Are there other states that have been predicted to form from these very high gluon densities? Okay, so the bottom line in red is need very low x, about 10 to the minus 4 or lower for x, the momentum fraction. Highly polarized beams, high luminosity, because you want to do 3D imaging of gluons in the nucleon, and you want to collide because you want these low x electrons in atomic nuclei. There are also new ideas that have come up in the last 20 years about generalized parton distribution functions and transverse momentum dependent distributions, which means that 3D imaging of the gluons would be quite helpful and interesting. And I don't think I will go into any detail here, except there's a proposal, although the location is not going to be determined for a couple of years, but this is Jefferson Lab in the US, in Virginia, proposing, they already have an upgraded electron machine. They would increase its energy and then put in, they would put in a hadron machine to make electron-hadron collisions, electron-ion collisions, and at RHIC kind of has the complement. Ideally, it'd be great if you could put them together, but they're 1,000 miles apart. RHIC has the heavy ion machine and would have to figure out a way, and they have various schemes, and I have to say these schemes have changed over the last couple of years. This is the latest, but in any case, they would build an electron machine to inject and have collisions with the RHIC beam. So, my last slide, lots of questions still. It's not like we know everything from what we see. We can't even explain a lot of the things. The initial state is quite interesting. Maybe we don't even get that from looking at proton-nucleus collisions and have to go to an electron-ion collider to understand the initial state with gluons in particular. We don't understand parton energy loss, actually, in perturbative QCD at the fundamental level. In fact, you expect that there should be differences if you have heavy quarks compared to light quarks. We haven't, and in fact, that's an emphasis of the program, both at LHC and RHIC over the next 5 years. Can we understand this Quarkonia melting, which I just showed you in a nice, simple picture, but can we understand it in a basic level and understand it in terms of even lighter nuclei and in peripheral collisions? There are many properties, of which I've only mentioned a couple, of the quark-gluon plasma that could be of interest. In particular, the bottom line would be, could we ever get to the equation of states of quarks and gluons as a function of temperature or pressure? So, is this phase diagram featureless? Are there new phenomena? Theory, there are lots of different developments in theory. They're all trying to predict what's going on with the measurements that we see. And you can go to the archives and see new ideas and new calculations almost weekly. I think the thing I have to mention is I didn't discuss in any detail the proton, lead, or deuteron gold data where there are some similar flow effects seen in the highest multiplicity collisions there. So that raises a whole other question. I could give, a 1-hour talk on these data and what it means, but it's not understood. We actually just had a retreat of some 30 people, physicists in our field, and discussed this. You know, is this hydro? There are people who say, well, you know, if you go to very high energy, even if you have protons, you could have enough constituents, gluons in particular, to actually see hydrodynamic effects. So, you know, this raises the question, really, what is the smallest droplet of quark-gluon plasma that's possible? And, you know, that's a very open question right now. All right, so I think the future of high energy density QCD is bright, and I thank you for your attention and participation.